For exercise 1.8, we're going to make use of the substitution z equals square root of y. Or another way to write that is y equals z squared. So in other words, our function that carries the roots to the other roots is f of z equals z squared. So this function f of z clearly carries the roots alpha, beta, and gamma to alpha squared, beta squared, and gamma squared. The problem is that f of z equals square root of z is not a one-to-one function. For example, what if alpha is like -1? Then alpha squared is going to be +1. The question is, does this actually matter? And we're going to find out that no, actually it doesn't. So let's just suppose that f inverse of z is equal to the square root of z. So we're only really defining the inverse function on the positive numbers, and we're sending it back to the positive numbers as well. And 0, I guess, although clearly none of alpha, beta, and gamma are equal to 0. So anyway, if we consider p of f inverse of z, where this thing here, of course, is p of z, then using function composition, we have the square root of z cubed plus 2 times the square root of z minus 1. And just doing a little bit of algebra here, this is equal to the square root of z times z itself plus 2 times the square root of z minus 1. And this should all equal 0 since p of z equals 0. And then from here we can actually go ahead and factor out the square root of z. So square root of z times z plus 2. And then bringing the 1 to the other side, we can say it equals 1. Now from this point, we can square both sides of the equation. We get z times z plus 2 squared, so z squared plus 4z plus 4. And then on the other side, we still have 1. And then expanding that out, we get z cubed plus 4z squared plus 4z, and then minus 1 equals 0. Now, you might not be trusting this little thing that we did here because it was, I guess, based off of this inverse function, which isn't really an inverse function. And maybe you're even sitting there going, what does this square root thing even mean if z is a complex number? And these are all good questions to ask. Let's do a little bit of reverse work here and actually confirm that the value z equals alpha squared does actually make this equation here true. And we can do it simply by using the first equation, p of z, where we know that alpha is a solution of it. So we do know that alpha cubed plus 2 times alpha minus 1 does equal 0. And then from here we can do something, well, we can do exactly what we did here. We can factor out the alpha, so we get that alpha times alpha squared plus 2 is equal to 1, and then we can go ahead and square both sides. So alpha squared times alpha squared plus 2 squared is equal to 1, and then if you just, well, at that point replace, at this point here, wait, no, which point? Well, yeah, at this point here, replace z with alpha squared, then you're good. It's just z times z plus 2 squared equals 1. And so yeah, we know this equation is the same as the one we ended up with down here. Z times z squared plus 4z plus 4 equals 1. So yeah, it ends up being the same equation, and we know that it works for z equals alpha squared. So we're good. Alpha squared is definitely a root of this polynomial equation down here. So it all works nicely, and alpha squared, beta squared, and gamma squared really are roots to this polynomial equation down here. But you may be sitting there wondering, why can we get away with this when this f inverse of z equals square root of z function isn't really defined on all the, well, isn't sent to the entire real numbers, for example, and we're not even really sure what it means for complex numbers. Well, the point is that it shows up in the working here, and from this step to this step, it actually, what we're saying here is that f inverse of z is, it's not really the square root of a number here. It's something that squares to z. So in other words, square root of z equals a if a squared equals z. So now we don't actually really care what a is. A doesn't have to be a positive number. It can be negative. It can be a complex number. But that's what we're going with at this step. Just supposing for a second that a was a negative number, well then we could take a to be the negative square root of z in the way that the function is usually defined. And then if we just put negatives throughout all the working here, we make the observation that when we go ahead and square both sides, it doesn't really matter whether there was a negative there or not. I mean, ultimately, you don't even really need to make this inverse function here if you don't want to. You can pretty much just go ahead and use this working here, which is just a trick of algebra, and we're going to see in a little while that it works for any polynomial, doesn't matter which one. But the point is that whatever the square root of z is, as long as it squares to give you z, then when we go from this step here to this step here and square both sides, that's when, it doesn't matter whether it's the positive or negative square root of z or whatever it means for the complex numbers, as long as when you square it, you get z.